Hey everyone, welcome to this explainer for your Programming Language Lab course. I'm absolutely thrilled you're here today. We are going to be focusing on Lab 3, C++ selection statements. You know, I always like to think of selection statements as the actual brain of your programming. Without them, your code is basically just a mindless robot, right? It just walks in a straight line, completely unable to react to its environment. But when you add selection statements, suddenly your code can think. It can adapt. It can actually make decisions based on dynamic inputs from the user. So whether you're totally new to this or you're a focused learner really wanting to sharpen those C++ skills, you are in exactly the right place. We are going to break down the logic, the actual syntax, and the real-world execution of all these essential concepts. Let's get to it.
Okay, really quickly, here's our roadmap for today's explainer. First, we'll cover the power of choice. Then, if and else logic. Third, we'll dive into nested and else-if statements. Fourth, we'll do a head-to-head comparison of switch versus nested logic. And finally, we'll wrap up with ternary and compound operators.
All right, Section 1, the power of choice. We are breaking out of sequential execution.
So to break out of that rigid, top-to-bottom sequential coding habit, we have to give our program the power of choice. Up until this point in your labs, your programs have probably run every single statement exactly once, right in the exact order that you typed it. We are going to change that today using something called a Boolean expression. You can think of a Boolean expression as the ultimate mathematical judge for every single decision your code will ever make. A Boolean expression is simply a condition that evaluates to one of two possible outcomes, true or false. That's it. There's no maybe, there's no sort of. It's binary. When we write an if statement in C++, the computer looks at that condition. If the condition evaluates to true, the code inside the block executes. But if the condition evaluates to false, your program completely ignores that block of code. It just skips right over it like it isn't even there.
Let's actually look at how this plays out in C++ code. Take our first example here. We ask the user for an integer, and we write a condition. Is this number greater than 0? If they enter a positive number, the condition is true, and the program prints out a little success message. But if they enter a negative number, the condition is false. The code block is completely skipped and the program just moves on. Now look at the second example. Here, we're trying to find the minimum of 3 integers by making a series of independent checks. We start by assuming the first integer is the minimum. Then we use a separate if statement to check if the second integer is smaller. Then yet another if statement to check if the third is smaller. By running these checks one after the other sequentially, we are guaranteed to find the smallest number. Finally, the third example introduces a simple game. We check if a user's guess is exactly equal to a preset magic number. We do this using the double equal sign. If the guess and the magic number match, boom, the program prints right guess. But think about this for a second. What happens if they guess wrong? Right now, with just an if statement, nothing happens. The program just ends. That's a little abrupt, right? We need a way to handle failure gracefully.
And that brings us perfectly to Section 2, if and else logic. This is all about adding a reliable fallback plan.
The execution flow of an if-else statement is just wonderfully logical. Step 1, the computer evaluates the Boolean condition inside the parentheses. Step 2, if that condition is true, the if block executes, and the else block is completely ignored. Step 3, if the condition happens to be false, the if block is skipped entirely, and the else block executes instead. It's like coming to a fork in the road. These are two distinct, mutually exclusive paths. Your program will walk down one path or it will walk down the other, but it is physically impossible for it to walk down both at the same time.
Applying this concept to code, let's check out our fourth example. We are checking if a number is positive using greater than or equal to 0. If a user enters a 4, the condition is true, so it prints positive integer. But what if they enter negative 4? The condition is now false, so the program instantly jumps over to the else block and prints negative integer. It catches the alternative. Now, looking at example 5, we can finally fix that magic number game we talked about earlier. We still have our initial check to see if they won, but now we've added an else block specifically to handle incorrect guesses. This is just a way better user experience. Instead of the program silently crashing or ending when they guess incorrectly, it politely informs them they failed, relying entirely on that else fallback.
All right, Section 3, nested and else-if statements. Time to level up into deep branching and complex decisions.
So the crucial takeaway here is that we can literally place an if statement inside of another if statement, or even inside an else statement. We call this nesting. You use nesting to build complex, multi-layered decision trees. I want you to think of it kind of like a security checkpoint in an airport. You absolutely cannot get to the inner set of questions unless you successfully pass the very first, outer condition. If the outer condition is false, that entire inner block of code is skipped, which actually saves your computer valuable processing time. Let's break down some C++ code for this. In example 6, we nest an even or odd check completely inside an initial check to ensure the number isn't 0. If the number is 0, that outer condition fails, and the inner even or odd logic is bypassed entirely. Pretty efficient, right? In example 7, if a user guesses our magic number wrong, we drop into the else block. But inside that else block, we've nested another if statement to give them a hint, telling them if their guess was too high or too low. And then there's example 8. Nesting allows us to eliminate variables one by one to find the minimum of 3 numbers. We check if the first number is smaller than the second. If it is, we dive deeper into the code to check if it's also smaller than the third. This nested logic structure is deep, it's robust, and it is a completely different approach than the sequential, independent checks we used back in example 2.
But as you might start to realize, sometimes deep nesting just makes your code look like a messy, unreadable staircase. That's where the else if ladder comes in, which you can see in example 9. Let's say we want to know if a number is positive, negative, or exactly 0. We start by checking if it's greater than 0. If that evaluates to false, we string an else directly into another if statement to check if it's less than 0. If that is also false, we just catch everything remaining with a final else block. Notice how beautifully this flattens out that nested code? The program evaluates these conditions top to bottom, and it will stop at the very first true condition it finds, skipping the rest of the ladder entirely. If you input a 1, it hits that first true condition and immediately stops. Input a -2, it bypasses the first, hits the second condition and stops. It's incredibly clean.
Moving on to Section 4, Switch versus Nested Logic. This is the elegant alternative for menus and exact matches.
Let's look at example 10. Here, instead of using greater than or less than inequalities, we pass a value directly into a switch statement using the modulo operator. The math here evaluates to exactly 0 or 1. We then literally use case 0 to handle the even numbers and case 1 to handle the odd numbers. But example 11, this is the absolute masterpiece of switch statements. It's a basic calculator menu. We ask the user for a choice. Type 1 for add, 2 for subtract, 3 for multiply, and 4 for divide. If the user types 2, the program jumps straight to case 2, does the subtraction, and prints the result. Now you need to pay very close attention to the break command at the end of every single case. This is vital. If you forget to write break, your code will literally fall through and start executing case 3 and case 4 automatically right after case 2, which would totally ruin your calculator logic. Also, take a look at the default keyword at the bottom. It works exactly like a final else block. If the user types a 9, which obviously isn't a valid menu case, the program hits default and safely prints an invalid choice error. The lab instructions specifically ask us to contrast these two structures, so here's your definitive cheat sheet. When exactly should you use nested if-else logic? Well, you use it when you are evaluating ranges of numbers, like say checking if a test score is greater than 80 and less than 90. You also use it for complex Boolean expressions involving inequalities, like less than or greater than. On the flip side, when should you use switch statements? Switch statements strictly test for exact equality against discrete, constant values. You literally cannot put a greater than symbol inside a switch case. Therefore, the switch statement is absolutely perfect for getting much cleaner syntax when you're matching specific choices, like keyboard inputs, menu options, or maybe specific days of the week.
Finally, Section 5. Ternary and compound operators. We are getting into the pro moves for writing really clean, efficient code.
Let me ask you a question. What if you could take a full 5-line, clunky if-else block and literally compress it down into just a single, elegant line of code? No curly brackets, no bulky keywords, just pure, streamlined logic. Are you ready for that? Because that is exactly what the conditional or ternary operator allows us to do in C++. The ternary operator basically asks the computer a question directly. Take a look at the syntax in example 12. We have our condition is x less than y, followed by a question mark. That question mark triggers the true or false paths. If the condition is true, we return the value before the colon, which is x. If it's false, we return the value after the colon, which is y. Whatever value is returned gets stored directly into our result variable. All of that logic happens in one single line. Now, example 13 takes this concept to the absolute extreme by nesting ternary operators. It squeezes our earlier minimum of 3 logic into one single powerful line. It asks if x is smaller than y, and if that's true, it triggers yet another question, checking x against z. It's a bit of a mind-bender at first, but once you read it left to right, it's incredibly efficient. But wait, we can actually condense our conditions even further using compound operators. To really master this, you have to understand the truth tables for logical operators. First, the double ampersand, that is the AND operator. An AND expression only evaluates to true if and only if both the left side and the right side of the expression are true. Next, the double pipe, that's the OR operator. An OR expression evaluates to true if either the left side, the right side, or both sides are true. It only ever fails if both sides are completely false. And finally, the exclamation mark is the NOT operator. It's simple. It just reverses the truth. If a condition is true, placing a NOT in front of it makes it false.
Let's move to example 14 and see how this all comes together to build our final logic comparison. Once again, for the last time, we are finding the minimum of 3 integers, x, y, and z. But look at the code. We've combined 2 conditions into one if statement. We are explicitly saying, if x is less than or equal to y and x is less than or equal to z, then x must be the absolute minimum. If that whole combined statement is true, we print x. If not, we use an else if to check y against the others, and finally, a default else for z. Contrast this hyper-efficient code with the sequential checks we did way back in example 2, or those bulky nested loops from example 8. By using compound operators, we made the logic perfectly straightforward, highly readable, and we didn't need a single nested block.
And there you have it. You've just seen the complete arsenal of C++ selection statements. You now have the power of choice. You understand nested logic, switch menus, and you've even got some pro-level ternary and compound operators under your belt. So my final question to you is this. Which logic structure will you choose for your post-lab challenges? Will you use the modulo and compound operators to calculate leap years? Or maybe you'll deploy a really clean else-if ladder to assign university grades based on score brackets. The logic is now entirely in your hands. Thank you so much for joining me for this lab explainer. Good luck on your upcoming assignments, and as always, happy coding.